Thanks everybody for joining us for this month's CARC Systems Facing Track presentation. My name is Dory Sidak. I'm with the University at Buffalo Center for Computational Research. Um, Today, we're going to be talking to you about a major project that we've been working on for about a year now. So I've been at CCR for about 20 years, and we've had several pretty major projects that we worked on where we really tried to not affect the users in any way. So we didn't want significant downtime. Sometimes we couldn't have any downtime at all. And we're changing the underlying HPC infrastructure in many of these cases. Sometimes we tried to actually make the changes or upgrades completely transparent to the users. Sometimes that worked, sometimes it didn't. But every time we've done one of these projects, I think this is impossible. We're never going to be able to do this. This couldn't possibly get any worse. I can't imagine any project more difficult. And then there's some other new project that comes down the line as soon as we're done with whatever we're working on. So about 2 years ago, we made two significant changes back to back. And I think a lot of you are familiar and had to go through the pain of changing CentOS 7 to something else, right? So we did lots and lots of research and testing, and then implementing those changes. That in and of itself created some challenges for us. We have a small support staff. We needed to keep the lights on and our users happy while going through this whole process of change. So to me, that particular project felt like we had this fully set table and we were trying to pull the tablecloth right out from under it. But we did it. It took about 8 months for us to fully transition, and we were able to keep the HPC infrastructure up the entire time. We slowly migrated racks of compute nodes over to the new operating systems, and we reinstalled hundreds of software packages. I can't even tell you how relieved I was when that project was finally done. It was like, okay, we could take a breath. And then this project came into our laps. And I really hope that this is the worst problem we will ever have to face, because if we do have to do something worse next year, it's going to be rough. But I'm going to pass it off to my colleagues, Andrew Bruno and Josh Furlani, and they're going to tell you the story of what we've done over the last year.
Okay. All right. Thanks, Dory. Hi, everybody. My name is Andrew Bruno. I'm here with my colleague, Josh Furlani. We're with the Center for Computational Research. And like Dory mentioned, we're going to be talking today about our experience expanding our research computing infrastructure to multiple data centers. So this has been quite the adventure, and we thought it'd be fun to share some of the more interesting bits about the project, how it came about, our planning process, some of the challenges we hit, and then we'll highlight a few of the tools we use to make our lives easier. And like Dory mentioned, we had to kind of tackle this project all while keeping our existing systems running. So we'll talk a little bit about that. Okay, so a little bit about us. We are the research computing infrastructure for the Center for Computational Research at the University of Buffalo. Our research computing infrastructure includes HPC clusters. So we run Slurm, batch queuing. We have a general compute cluster that is available to all researchers at the university. We also do faculty condo clusters where faculty can purchase their own nodes, and we install them and run it, and they get exclusive access with no wait times. We also do an industry outreach. So we have a cluster dedicated for our industrial folks. We do high performance storage. We're a 100% VAS shop. So we use VAS for user, project, and scratch space. We also run two Ceph clusters, one for our Proxmox virtualization infrastructure that runs our core services, and one for our OpenStack cloud. So we have that. The use case for our cloud, is for the researchers who don't necessarily, their workflows don't necessarily fit the batch queuing model. Maybe they need like 24/7 access or root level privileges. We have a private, locally hosted cloud that they can leverage which provides some features similar to like, the public clouds like Amazon. We do a lot of user support. So our staff, manages 2,000 user accounts, 500 PI groups, 1,000 allocations. Our staff builds software environments. So we use Easy Build. We distribute the software with CVMFS. We've been doing a lot with containers lately, so we've been trying to roll out Podman as our container runtime, which has been interesting. We run on demand. We work closely with the OSC folks on that project. Recently, we've been doing a lot of training too. So we started to work on some introduction to HPC, like self-paced courses that are available for our users, which we've been rolling out with a lot of success. And finally, we do a lot of open source development. Two of our probably more popular projects are XDMod, which is an high performance computing metrics infrastructure. And then we also run ColdFront, which is an allocation management system. And super excited, ColdFront recently just got funded. So if you haven't checked out ColdFront, definitely encourage you to check it out. Come join our community. We're really trying to build up a good community around there. So check it out. Okay, so UB has 3 campuses. We have our North Campus, which is kind of like our main academic spine, and that is north of the city of Buffalo. We have our South Campus, which interestingly is technically in the kind of northeast corner of the city of Buffalo, but it's south of North Campus, so we call it South Campus. And then we have a downtown campus, which is more in the downtown Buffalo proper, and that's where we live. So that red arrow there, that building, that's where CCR's data center is. And I don't know if you could see, but behind there, that orange building there is our new medical school that was just built. So we kind of live in the medical campus section of University of Buffalo, which is kind of a cool place to be. So next slide is, this is a shot of our data center. And it is a 4,000 square foot facility. It has a raised floor design. So all the power and the cooling and the cable management, everything's under the floor. We've got about 30 tons of cooling, 600 kilowatts of max power in there. And we manage about 40 racks-ish. And we've been here for almost 20 years. So why did we decide to expand to another data center? Well, I'm sure everybody can appreciate, this thing called AI came along, and it came with some serious massive power requirements. So we just wanted to include this kind of some of the power upgrades that are happening in our data center. So this is the power feed that's been coming in. I mean, the power requirements for some of these AI clusters are just incredible. So it kind of forced us to, think about multiple data centers that we'll get into. But in particular, there was a project that came about that was launched in 2004 by the state of New York called Empire AI. And this is a consortium of public and private research institutions for advancing AI research. And one of the kind of objectives of this project is to build a new AI computing facility that will be housed at the University of Buffalo's North Campus. And as the project got going, it was kind of decided, because it's going to take a couple years to build this new building, that Empire AI would be rolled out in phases. So the first 2 phases, phase 1 is called Alpha, and phase 2 is called Beta, are going to be these fairly large AI computational clusters. And these clusters are going to be housed and installed at CCR's downtown data center, some of the pictures we just showed. So CCR was tasked with kind of coordinating this, because it was our facility, so we had to kind of help with the physical, where is it going to go, kind of capacity planning for the first 2 phases of Empire AI. So given tasks with that, we got together as a group and we created a project plan. And of course, all project plans need an awesome name. So we decided to adopt the opossum as our mascot, because, fun fact, the opossum's brain can automatically send its body into this comatose state as a reaction to stress. And that's pretty much exactly what happened to us when we first heard about this project. So we figured the name seemed fitting. But there was really two objectives of this operation, right? The first is we needed to install both the first two phases, right, alpha and beta of Empire in our current downtown data center. And there was lots of planning back and forth on this, but basically the power requirements for these clusters were so big, there was really no other locally facility that we could put this cluster in. So we decided to upgrade our current downtown data center, put the clusters there. And then whatever would not fit in our existing infrastructure would be expanded to a second data center. So we're going to start doing multi-data centers. Those were the two kind of goals of this. And in the background there, you can kind of see some of the transformers and stuff that is being added to our facility just to accommodate the crazy power requirements for this. So for the rest of this talk, we're going to kind of highlight three parts of this project plan. So the first, we'll talk about the power and cooling capacity planning that went into deciding, where is alpha and beta going to go, and then of our existing assets and infrastructure, what to move. And then we'll talk a little bit about how we actually moved that infrastructure. And then finally, we'll talk at a very high level, we'll just go over our multi-data center network design. So now I'm going to pass it to Josh, who he'll go over our power and cooling capacity plans and how we kind of decided how we could fit all this stuff.
Thank you, Andrew. So can we fit the alpha cluster? Well, we're going to need some numbers first. Alpha was to be comprised of 4 racks of compute, 12 H100 HGX nodes in total, with 2 separate 2 petabyte high performance storage clusters. That adds up to a total of roughly 130 kW. And well, Alpha was already successfully launched in October of last year and ranked number 283 on the June top 500 list. But how did we decide if we could fit the Alpha cluster? Well, what does our current power infrastructure look like? We have 3 220 kilovolt amp UPS units, which were original to the building. These were designed to run in an N+1 mode, which would allow one unit to be shut down for maintenance. However, we had already exceeded that capacity and had to change to N+0, giving us our 600 kW 90% maximum. Compute node max power numbers from our vendor show that we would be well over 600 kW without alpha. However, vendor max is not real world max. What you're looking at here is a graph of our power consumption. Each bar represents a rack sorted by most to least power. And we were able to utilize this power monitoring from our PDUs to calculate how much power our compute infrastructure was actually using. This showed that we should have enough headroom to power alpha on, and so we did. The alpha cluster hits peaks of a little more than 100 kW. This graph shows sampled data. We also monitor our UPS units themselves. This allows us to see the full picture of how much power we are consuming, including factoring in any devices that are outside of our control. You can see that from the graph on the bottom that our power usage can regularly swing plus or minus 100 kW. And that yellow dashed line represents 80% of our UPS's maximum, which was now regularly being crossed. After alpha was online, our peak output power was just shy of that 600 kW maximum. We were certainly at capacity. Cooling is another important factor, which I won't spend too much time on. Our room was designed with more cooling than power. We monitor temperature from both our CAC units as well as from our compute nodes intake and exhaust sensors. This was used to make sure that alpha was placed in a good spot, which wouldn't imbalance the room's cooling. Our nodes BMCs were set to automatically power off if their intake temperatures got too high, which would be an indication of a cooling room failure. In that scenario, we would want our switches, core services, and storage racks to operate as long as possible before shutting down. Ask us how we know. It might have happened once or twice before. Now, where does all this data come from? Well, we use Prometheus and Mimir to collect and store the data, and Grafana to visualize and provide alerting. We do publish some of our own custom Prometheus exporters, but most of what we cover today will be scraped via SNMP. It was absolutely critical we had this monitoring in place to be able to make decisions off of actual data representative of our use case. So what about beta? Can we fit it? Absolutely not. The beta cluster is set to be much larger than alpha, more than doubling our entire compute infrastructure. The rough numbers include 600 kW of GPU compute with just the GB200 NVL72 cabinets, on top of which there will be NVIDIA Grace CPU compute nodes, and the alpha cluster will gain 12 more HGX nodes, half with H100 GPUs, the rest H200 GPUs. And that leads us into our data center expansion, which I'll hand back off to Andrew.
All right, thanks, Josh. Yeah, so how, like Josh mentioned, we were not able to fit. We knew we weren't going to be able to fit alpha, beta, and all our current existing infrastructure. So we decided to expand to a second data center. Next slide. Let's see. Yep. So beta required us to expand to a local tier 4 co-location facility that was I think it's just 15 miles away from our current data center. So what we wanted to do was come up with some scope and requirements to this project, because we wanted to help some of these things drive the rest of the decision-making process. So I thought it'd be good just to highlight just some of our thought process and some of the goals that we wanted to achieve in this project. So the first kind of hard requirement we came up with that really anchored the rest of our decision-making was that we wanted to minimize the downtime and impact to our users. We really did not want this, this expansion to really affect them. Ideally, they wouldn't even know that, things were moving around. So that really was probably the most important thing. The second was we knew we had to move some racks around. We knew we had to expand to this second data center. So we wanted to make sure we were able to identify which racks would really give us the most bang for our buck. How could we move those things around in the most optimal way? The third was moving to multiple data centers. This was kind of our first experience with this. For 20 years, we've been in a single place. So we wanted to make sure from a networking perspective that we had connectivity between both sites, in terms of like running jobs, copying files, anything at the network layer was just very smooth, and it basically appeared as a single site. So that was super important. The other big driver that we had to decide early on, which I think most people here can appreciate, right, is what do you do about your core storage? And we made the decision early on we're not going to move our core storage for a couple of reasons. The first was that it would have violated our first requirement, right? It would have required just a lot of downtime. Your core storage is just the backbone of everything. So moving that would have been, a substantial amount of downtime that we just weren't willing to take. And then the second reason was just risk. I mean, physically moving, your core storage, if something happens where, hard drive breaks or you start losing data, we just didn't want to go there. So what we decided to do is we purchased a new VAS cluster for the second facility, and we are leveraging some of VAS new features called data spaces, which allow you to do a multi-site storage cluster. And finally, we wanted to put our forward-thinking goggles on, right, and think, okay, when we, in the future, when we decide, maybe we purchase a new cluster, we want to build and design this such that if we have spare capacity, for example, the downtown data center, we can put the new resources there. If we have spare capacity at the new facility, we'll put it there. So having that flexibility to put resources at any location was important to us as well. So now we'll talk about the physical move logistics. So how did we actually expand our infrastructure to the second location? And before we, before we could identify even, what racks to move, we had to figure out how we were going to actually move them. So, we tossed around a couple ideas. Are we going to take all the nodes out of the rack, put them in a box, right? Ship them to the new place, and then put them in a new rack. Was there any potential for maybe moving full racks? So we worked closely with the co-location facility that we were moving into, and they've been great. So typically the way they operate is they give you a rack, and they provide all the power, they provide the cooling, and then you basically own everything inside the rack, and then everything outside the rack they own and operate. But one of the concerns we had with that was just the amount of labor it would have required to, remove all our nodes. We have all InfiniBand cabling and Ethernet cabling, all that craziness is in there. To just rip all that apart and then, move it over to the second location, we thought, okay, well, that could require significant downtime. So could we move the full racks? And again, the co-location facility, they were awesome. They ended up building out a whole suite for us, and they allowed us to bring our existing racks over there. So we decided to move the fully loaded racks. And that presented two additional challenges, right? So the first was our existing downtown data center ran on single phase power, and the new co-location facility was 3-phase power. So that required us to buy and swap out all new PDUs in our racks. And then the second thing was the issue of rack density. So the co-location facility, the racks that they use are a little bit larger. They do a better job of distributing the weight, and they also limit how much you can load up those racks for weight reasons. Where our racks are kind of fully loaded, we put as much as we can in there. Some of these racks can weigh up to 1,600 pounds. And this presented a challenge for actually placing these racks at the new facility. So this picture here, if you can see on the left-hand side, is a shot of the new co-location facility we moved into. And on the left there, you'll see those white racks. Those are the racks that they typically use here. On the right-hand side, that black rack there is our racks that we currently use. So you can see they're just totally fully loaded. And the structural engineers at the co-location facility were concerned about putting all these racks and how they would affect the weight distribution of the floor. So what they did is they designed a rail system. So if you see on the bottom of this picture here, there's these two gray rails. And what they needed to do was lift these rails and place them on, lift the racks and place them on the rails. And to do that, they hired a company that fabricated this monstrosity here on the left. You can see this kind of, I don't know if Josh can annotate the screen there, but they built this rig to lift these racks. So on the right, you'll see those orange pulleys. So what they did is they fabricated these metal bars that bolted to the top of the rack. And then they actually lifted the rack, slid it over on this rig, and then placed it on the rails. So this was kind of crazy because when Josh and I first came to the facility and we were installing our networking gear in those white racks, we passed this huge rig there and we were like, what the hell is this? Like, why is this thing in the way? We were just kind of joking out, it must have been for the electricians or something, And then we were talking to the facility later and they're like, oh yeah, we need to lift your racks up. And we're like, say what? Like lift our rack? What are you talking about? So it was just, kind of mind boggling when they were like, yeah, we're going to lift your 1,600 pound rack and put it on the rails. But the company that did this was phenomenal. There was no problems. I mean, we were thinking, lots can go wrong when you're trying to lift these fully loaded racks, but we had no hiccups and it all worked out pretty good. So it was kind of an interesting part of the process. So now that we figured out how we were going to actually move the racks, right? Now we had to figure out which racks we were going to move. So how did we identify what assets to move? Well, we definitely took a data-driven approach. And like Josh was talking about, we leveraged all the power metrics that we were capturing from Prometheus. So, here, we know how much power each rack's taking. So we were able to identify the most power-hungry racks. And figure out, okay, well, if we move these guys first, that'll free up a lot of our power budget. So, let's figure out which ones to do. On the next slide, you'll see that we went through several iterations of this. So this is a diagram we used quite a bit in our planning process. This just shows all our current assets. This is a shot of our downtown data center. We did lots of studies on the airflow, the hot and cold aisles. Where are we going to put alpha system? Where's the best place to put the beta system? What existing assets are in those locations that had to move, which ones were the most power hungry. So it was kind of crazy. I just wanted to mention too that while all this is going on, we're us trying to figure out, which assets to expand to the second location. We have electricians in the data center and plumbers doing, upgrading this in preparation for the beta system that's coming. So this was just kind of a giant chess game of how do we move what. So it was kind of wild, but we boiled this down to 3 moves because we knew we had to move about 17 racks. And we decided to do it in 3 separate moves, about 5 to 6 racks each. And we wanted to do this over a 4-week span. So to give you an idea about how a typical move went, next slide. Each move took about 2 days. And let's see next, yeah. In terms of user impact, there was about 32 hours of downtime. So we were able to get this down to pretty much less than a day and a half. And to give you an idea about the days, right? The first day was rack prep. So we would set the racks offline in Slurm, power them down, and then, like we mentioned before, we had to swap those single-phase PDUs out for 3-phase PDUs. And then we did some, kind of in-rack fiber cabling. So we added some patches in preparation for some of the new network changes we were making. We did a bunch of relabeling, right? Because when the rack would go offline in one data center and it'd be moved to the next data center, it would have a new name, it would have a new network configuration. So that was kind of day 1. And then the second day, we had scheduled movers to come. Next slide. And they would they would be there at 8 o'clock. They would load the racks on the truck, bring them over to the second facility, unload them. They would wheel them up into our suite, where they were met by the company that actually lifted the racks. So then they would take over. They would rig up the racks, lift them up onto that rail system that we showed before. And then as soon as the racks were set in place, that's when we would come in and we would do our fiber cables. So we'd run our fiber cables to the racks back to our spines. And then we would energize the racks. And then we had everything set up to automatically provision. So the switches would come online, they'd get their new configs, compute nodes would get their images, and then they were back online running jobs in Slurm. And to give you an idea on time, it was basically, so that second day there, the movers were there at 8 o'clock. Most of the physical move, setting the rack in place, wiring things up was done by about 2 o'clock in the afternoon. And then from energizing the racks to running jobs, they were back up about 4 o'clock. So we got the process down pretty good. And just to touch a little bit on our compute node provisioning and our provisioning system. So we use some of the tools that we use for this are, we use NetBox for our data center infrastructure management system. So we model pretty much everything in NetBox. All our switches are zero touch provision. So they, when they turn on, they get a config. That's all automated. We do this using a tool called Grendel, which is a provisioning system that we actually developed in-house at CCR. So Grendel has integrations with NetBox. It does, it speaks the DHCP protocols that require, the PXE booting and the automated provisioning. We're actually super excited about, kind of growing this project too. So if you have any interest in provisioning systems, definitely check out Grendel. This is a screenshot of NetBox. So NetBox is like a huge tool. This really doesn't, the screenshot doesn't really give it justice, but I just wanted to show you at least a little bit about how we use this tool. So on the right there, again, we model everything. So this gives you a shot of like the front and the rear of a rack that's modeled. So all our compute nodes, our switches, our PDUs, everything's modeled in here. You can click on a device and configure it. Again, all the configurations are modeled in NetBox. We can do, kind of power utilization because the PDUs are in there with the circuits and where they're plugged in. Every fiber cable's modeled in here. So it's just it's a fantastic tool for, and we really couldn't have done a lot of this stuff without NetBox. And then we use Grendel for provisioning. And this is just a tiny screenshot of the Grendel web interface and some of the features. So again, we do all our automated provisioning. So all the compute nodes are provisioned through here. Same with the switches. So when a switch boots up, it reaches out to Grendel for a DHCP address. It says, hey, I want a ZTP. Grendel then reaches out to NetBox to render the actual configuration for the switch. Sends it back to the switch, which zero touch provisions. Compute nodes are done in a similar fashion. We can do power control via Redfish. We do all the iDRAC configurations through Grendel in an automated way. We update our PDU firmwares. We can manage boot images. So there's just a lot that we can do with this tool, and a lot of other features that we're hoping to build in the future. So so that's a little bit about our provisioning. So next we'll switch gears to talk finally about, at a very high level, our multi-data center network design. And we figured we weren't changing enough things, so why not completely redesign our network, right? Why not add that to the project roadmap? I mean, but like in reality, there's really never a good time to do this. There's never a good time to say, okay, let's take our network down and rebuild it, and we'll just be down for a couple weeks. But we figured, adding this second data center was a very good opportunity to take a fresh look at our network topology and make some much needed changes, especially now that we were kind of adopting this multi-data center network design. So here it just highlights some of the goals that we had for this redesign. So I'll just go over real quick. At a high level, we wanted to move to a layer 3 spine and leaf topology. We wanted our spines to run on commodity hardware that was easy to replace. We mentioned before, just very briefly, that we run Proxmox, but Proxmox runs all our core services. So it runs, our DNS, our Slurm controllers. We have a ton of infrastructure on here. And in moving to this multi-data center design, we wanted to ensure that we had the ability to live migrate those services across data centers. So that was very important to us. We wanted to ensure that we had also some redundancy with the data centers, so that if something did happen to one of the data centers where, I don't know, maybe we hit some power limits and things went bad, that there was no kind of dependency issue. Like we could always get to the other data center and kind of troubleshoot things. So having that like redundant path for external connectivity was important. And then finally, most importantly, because we had to do all this while all our existing systems were running, we had to make sure that nothing in the existing topology broke, right? Because everything's still, jobs are still running, so nothing can change really there. So how did we go about implementing this new topology? So first, this is a very quick diagram of our current existing old flat layer 2 topology. So the way we had pretty much been running for the past 20 years, we have a big fat core switch, a big chassis switch that has a bunch of blades. All the racks and the leaf switches there connect back to this single core switch. And everything is just layer 2. So what we did first was we built a new layer 3 topology as a parallel network. So we added a service rack with a pair of border leaf switches that served as the start of our layer 3 topology. And we connected our existing layer 2 core switch back for that seamless connectivity, so that we kind of bridged this parallel network together. And by standing that up in parallel, we were able to kind of minimize those configuration changes to the old core switch that was still running our entire center. And then we continued the build out of our layer 3 topology at the new data center. And we added another pair of border leaves and connected those together over 4 100 gig links using DWDM. So that served as our inner data center connectivity. And then we built out our new layer 3 spine and leaf architecture in the new data center. So on the right-hand side there, you can see we have 4 spine switches. That runs BGP, and layer 2 is terminated at the top of the rack switches. all those 4 spine switches. Oh wait, go back. Yeah, all those 4 spine switches still, they ran on commodity hardware. So we can easily swap those out. To give you an example of why that was important to us, was our old layer 2 topology there had that big fat core switch, right? And it was just super expensive. Those switches are not cheap. So every 5 to 10 years when we would upgrade it, it would be this humongous purchase. And anytime if you want to make any changes to those configs, there's this risk that, well, it's the central point of failure, so it can take your entire network down. So in this new design, we wanted the ability to first, those 4 spine switches are just commodity switches. If something happens to them, we can take one out, plug one back in, it'll automatically get its config, and there's no downtime. So that was one of the things that we wanted to do. Also, we wanted to optimize the east-west traffic between the racks. So each compute leaf switch connects back to all 4 spines, and we use ECMP. So that was another thing we were trying to tweak with this new design. And then finally, the Proxmox VMs, we talked about that. So that those border leaf switches run VXLAN, so we're able to live migrate between the data centers. So now, we can even do auto failover if there's some issue in one data center. We can have core services auto failover. And then finally, on the edge there, those red boxes, that's basically our connectivity to the outside world. So that runs our NAT gateways and our firewalls. So there's those red lines are actually redundant paths to the outside world. So taking this parallel network approach really allowed us to have a smooth transition to our new layer 3 topology. And through attrition, right, when we take racks out from our data center 1, right, and move it to data center 2, where it goes from L2 to L3, slowly we won't have as much stuff on that old network, and it won't be as large of a downtime to take it out, reconfigure it to full layer 3, and we'll be all migrated over. So that helped us out. And again, so I stayed super high level here. I didn't get into, there's a lot of other details, but I didn't want to get too down in the weeds. But if you're interested, we're happy, just feel free to ask a couple questions. We're actually happy to deep dive on any aspect of that. Next, I'm going to turn it over to Josh, who's going to talk in more detail about how we did the physical wiring of all this new network infrastructure.
Thank you, Andrew. So yeah, how did we wire it all up? Well, our downtown data center, we previously did individual fiber runs using pre-terminated active optical cables. At 2 to 4 core fibers plus an out-of-band connection, we had quite the mess under the floor. Tracing cables wasn't fun, labeling cables wasn't fun, tracing mislabeled cables was even less fun. Removing old cables was tedious because of how tangled everything would become, on top of having to pull a giant QSFP connector through the tangle. All of this led to needing a cleaner solution. Along came structured cabling. This design would reduce the fiber runs to each rack down to a single MPO12 cable. On each end of the cable, we would use a breakout cassette, which would give us 6 LC fiber pairs, 4 of these being used for the spine uplinks and 1 for the out-of-band management. The network rack side of these cassettes are located in the patch groups pictured in the middle of the diagram. The patch spines, which are racked below the patch groups, are used to break out the 400 gig spine ports into 4 100 gig LC connections, since our leaf switches are using 100 gig uplinks. Now, what about cable labeling and tracing? Well, we can utilize NetBox for that. Everything you saw in the previous slide is modeled digitally in NetBox. This documents our entire network topology and allows us to see where cables are connected without physically standing in front of them. In order to map these digital cables to the physical world, we use the serial numbers and barcodes already printed on each cable that we buy. This allows us to scan any network cable in the data center and see a full end-to-end cable trace as pictured in the left image. No more printing labels with names that will become outdated and inaccurate. And a quick note about data center design. As mentioned, our downtown data center is a raised floor design. We run both our networking and power under the floor to the racks. The co-location facility has power sockets mounted to the ceiling and an overhead cable tray for the networking. Although we have not spent nearly as much time with the overhead cabling, I can say that so far I much prefer moving a ladder to 40-pound concrete-filled tiles.
Okay, thanks, Josh. Yeah, so this past year at CCR has been, been pretty crazy. We literally have been changing the tires on a car going 4,000 miles an hour. But anytime you change something, it's just hard, right? Especially with when you're in a data center or you're in one location for 20 years, there's just 1,000 little assumptions that you make, right? You're like, oh, well, we're never going to have a second data center, so let's name it this way or let's design it this way. And then all of a sudden you have a second data center, and all those assumptions that you made, that legacy stuff just creeps up on you. So it can get really messy, and changing things just gets super hard. But I think overall, or actually, it's funny because like the whole time you're doing this too, you're like, oh, it's going to be so great once we're done. It's going to be amazing, and it feels like you never get there. Because you're always like, oh, we're almost there, but something else comes up. But I think overall, this project was a success to this point. We're not quite at the end yet, but we've successfully moved 17 racks. We've had minimal downtime, and we were able to get those 3 moves down to a day and a half. Let's see, next slide. This is a picture of our racks, the new location. So they're all happily running Slurm jobs, humming away. And again, so in terms of like user impact, we actually haven't heard much from our users, which we're taking as a good sign, because we figured if we don't hear anything, that means, that not a lot of people have been bothered. But if we start hearing a bunch of things, then, we're impacting them. So overall, I think good things. So really quick, we'll just highlight some of the lessons we learned. So first, monitor everything. Having those detailed power metrics allowed us to make really the data-driven decisions we needed to make to figure out how we can best expand, and then ensure that we were operating within the power limits. So, making sure when we added the alpha cluster that we weren't over that power budget. And if we did, we could take appropriate action. The second thing was, did moving the full racks really save us time? It probably did. But in hindsight, those new racks at the co-location facility are really nice. We like them a lot. They're better, they're bigger, the cable management's better. So in hindsight, we probably would have been better off moving the nodes into those racks, even with the slight increase in labor time. But it is what it is. The third one is automate everything. We invested a significant amount of time into automating our deployments. On switch level, on compute nodes. This really allowed us to, the actual move just took the physical time. As soon as we energized those racks, they were up and running. When we didn't do it, it was all hands off. But that was because we spent months automating all that. But it's well worth the investment, and really helped make this transition much smoother. BGP in the data center is pretty awesome. We're pretty happy with our new layer 3 network design. It definitely has a steeper learning curve. There's a little bit more protocols involved, but overall the L3 spine leaf was pretty easy to deploy, and I think it provides us some flexibility for the future. So pretty happy with that. And then the last thing was just multi-vendor networking is really hard. So given our budget constraints, we don't have a big budget, so we don't have the luxury of buying from a single vendor. So over the years, we've accrued Arista switches, Dell switches, we have Sonic switches, we have to support Dell OS 10, we have to support Sonic, we have to support EOS. That proved to be very challenging, especially when you move to the more complex routing protocols. So I guess if it's possible, use a single vendor. So where are we headed in the future? So we're actually only half done at this point. We've now identified 13 more racks that we're going to expand to our second facility. But we got the process down now. The movers know where to go. They know what elevator to take. The rack lifters know how to lift the racks. They can do it pretty quick. So we're feeling pretty confident about it. The Empire AI beta system will be coming online soon. So there's lots of exciting stuff going on in our data center right now, our downtown data center. So lots of cool stuff there we're excited about. And then this month, a couple of weeks here now, we're going to be bringing our second VAST cluster online. So we're really excited to start playing around with some of the multi-site VAST capabilities. Here's some links to the tools we talked about. And then again, just like to take a moment and thank the system-facing team for inviting us to talk today. thanks everybody for your time. We did stay super high level, but we just want to kind of give an overview of our experience. If there's any questions, we're happy to deep dive or answer them. So thanks so much for your time.
Yeah, thank you guys. So we do have a few questions, it looks like, in the chat. David Williams was asking, he just had a simple question. He was asking what Sonic was.
Yeah, so Sonic is I guess it's an open source network operating system that I think there was a bunch of companies involved. I know Dell was involved and Facebook maybe and Google, but it's an operating system that runs switches. So it's kind of like Dell provides Dell OS 10. Arista has their own operating system called EOS. Sonic is supposed to be a little bit more open source and run on more platforms.
Looks like a quick follow-up. Do you run it on your new spines?
We do. Yes, our
Okay.
spines run Sonic. Yep.
Okay. And then another question from Amir. They said, amazing presentation. Did you use any metric exporters for the power consumption per rack? And could you elaborate on that, please?
Sure, Josh, you want to take this one?
Sure, yeah. So we do it in two different ways. We query the BMCs that run on the nodes themselves to get their power, the individual node power consumption. And then all of our PDUs that we have, both the single phase existing units and the new 3-phase ones, are metered for their total input power. So for the graphs that you saw in there, that would be off of the PDUs, just queried via SNMP.
Okay, then looks like we have another question from Feng. Can you please compare Linux module with EasyBuild and CVMFS?
Compare them. So like,
I think they're looking for possibly a difference between LMOD module hosting and CVMFS.
Okay. Yes. Yeah, I can touch on that a little bit. So EasyBuild actually builds LMOD modules. So it's just an automated way of building out those modules. CVMFS we use, it's basically a distributed file system. It's read-only, so it allows us to distribute the software a little bit easier. It's not really reliant on our core storage. It's also read-only, so when the software is being used, it can't be changed in any way. So I guess it's just a different delivery mechanism. But otherwise, EasyBuild is just an automated way of building software that the output of that is LMOD modules.
Cool, thank you. And I just sent a reply to your message, Fang, but if you'd like to elaborate on your question, if I misinterpreted it, please turn on your mic. Cool.
Oh, that answered my question. Thank you. Yeah.
Okay, cool. I'm glad. Are there any other questions at the time? All right. If there are no more questions, I will let you take it from here, Dory.
Thank you, everybody, again for joining us. We appreciate the platform to talk about one of kind of our crazy stories. I personally always enjoy hearing the war stories. There was a great track last year at PERC where people just talked about in the trenches work that they did. And I say that we did this project, and that is just not at all accurate. Andrew and Josh did all of the work on top of managing different deliveries for Empire AI and new equipment for faculty. And one thing that we didn't touch on at all, because it's not really specific to CCR, but the location of our data center in the university building is quite a long distance from where the actual equipment is dropped off. So we're attached to one of the hospital buildings, which has a loading dock, and that's what we use. So anytime we want to get equipment, we have to take a nice long walk all the way to the loading dock, which also has a pretty decent angle as you go down one hallway. So if you're coming down with a very heavy set of equipment, it's a little dicey. If you're trying to push the equipment up that nice ramp, it's also difficult. So there were some complications with having all the new UPS parts delivered, and also the new NVIDIA system, the beta system, is much taller than the doorways that go all down the hallway. So all of those doorways had to be replaced. And so there are a lot of people and a lot of departments and actually three organizations involved with all of these changes. So it's been quite a ride. And I'm sure Andrew and Josh are ready to be done with it. So anyway, thanks again for letting us tell our story. And we'll see you. We will not see you next month in November. We will not have a systems facing meeting because of supercomputing. And then in December, we will be joining together with the rest of the CARC system facing groups to have kind of a holiday party, which you'll get more info on in your email after supercomputing. Thanks again. Have a great day.
Yep. Thank you very much.
Thanks,